Here we go. Okay, 18.1 notes. So last chapter that we would have gone over, that we are going over, is on equilibrium. And equilibrium just means equal rates. It's a balance point. Okay, so when something's at equilibrium, that means that it's balanced here. So in order to have a balance, we have to have two sides going on. So we have our normal reaction where we have our reactants and our products, and these are forming products, right? So the amount of reactants usually just goes down and the amount of products goes up, and that's all we've been talking about so far. But if it's reversible, then once we start making some product, some of that product will reform reactant. Okay, so the reactants will kind of like unreact, you could say, and they will form more of the reactants. So we have this weird balance point that will eventually happen. And if you guys watch the video, it's a really good visual of when you take the cups and you're taking from each beaker and pouring it into the other one. If they're equal rates, the amounts in the beakers won't change. Even if they were not equal amounts. So even if I had a whole bunch more reactant and very little product, if I'm scooping the same amount and doing this, then as long as the rate is equal, the amounts won't change. So equilibrium doesn't mean equal amount. It just means equal rate of change, okay? And remember from last chapter, the way that we measure the rate is by looking at how fast the reactants are going down or the products are going up. The rate should be the same for those things. So it's basically, it's the slope of the graph. And in an equilibrium, it's going to start out fast. The reactants will go down quickly, and then they'll kind of level off. And when it's at equilibrium, they remain constant. That's how we know it's at equilibrium. Okay, I'm going to go ahead and draw that for you guys. I'm getting ahead of myself, but let's go with it. Okay, oh, where's my picture? There it is. Okay, how do I get a new page? Open. I want to graph this for you. Keep. And paint. Okay, so we had our reactants, which let's make them green. And they are going to go down. So they start somewhere up at the top at a high concentration. And then they go down quickly and it starts slowing down. Notice the slope is getting smaller and smaller and smaller. And then eventually it does go up and down. So this is my ugly graph, but it also actually does do that because it's still reacting and unreacting, but they just are in equal amounts. So you don't really see it. And here's my product. I had none at the beginning, so I'm going to start at the bottom. And it should go up at the same rate. And then it's going to start leveling off like this one did. And sometimes a common misconception is that where they cross right here, this is, I should have labeled my axes. This is our concentration on the y-axis. So I'm going to label this B. Okay, and the green one is my A. And then the reaction is actually A, can form B, but since this is a reversible reaction, B can then reform A. So this is the symbol for a reversible reaction, showing the arrow in both directions. A lazy way of drawing it is with like a half arrow like that. And this is usually what we use in the classroom, and you'll see this a lot in videos. This is also a reversible reaction. So it's just drawing the arrow without the bottom part. Okay. So this is our reaction. A decreases, B increases. Right here, this would be equal concentration. So if we had really easy numbers like in our simulation, I told you to start with about 100 green A molecules. And if they're going down, 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 and this is going up, 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 when they reach this point, it could be, it's not necessarily, but it could be at 50, 50. So they're going to be present in equal amounts. Okay. So for this one, if I start with 100 and they're equal, then they have to be 50, 50, because there's going to be 100 atoms in their total. So that 50 point is just kind of a random spot where they happen to be equal, but this is not equilibrium. Time, down here, we would have all the little tick marks for time, and where it actually reaches equilibrium is where they stop changing. So I still see a slope right here. I don't know if you guys do. And this is still kind of has a little slope, so I'd say about right here. About right there, whatever time that is, let's call it T with a little E for equilibrium. Whatever time that is, that's when it reaches equilibrium. So over here, everything on the left side, this is all of our rate law stuff, where we're talking about how fast is the reaction happening. This was time 0, the very beginning of the reaction. We call that initial. So the initial reaction rate is going to be really fast, and then it slows down. This whole chapter, we're only worried about this right-hand side of this equilibrium point. So this over here is, I'm going to put a big E for equilibrium. E is for energy, so I'll put a Q. This is our equilibrium over here on the right. And this is what we're worried about. Okay. And let's go back to our notes over here. Oops. So for dynamic equilibrium, the word dynamic, you guys should have thought about. If you didn't, think about it. What does dynamic mean? Have you thought about it? Dynamic means changing. So if you're a dynamic speaker, you're going to use your hands, you're going to use your tone, you're going to use volume to change whether you're talking softly or talking loudly. You're dynamic, it's changing. If you're monotone, then that's not dynamic speaking, right? You're keeping your tone the same, the pace is the same, everything's the same, and that's not dynamic, okay? That would be static. You're a static speaker. All right, so what does this mole have to do with anything? It's kind of weird, and I wanted to draw on it, so I put it over here in my other Google Keep. And I can't draw on this drawing. Oh, man. Okay, well, picture them all. And you guys know I can't draw in real life, so let alone my virtual whiteboard over here. It's going to be pretty ugly. Okay. And here's my mall. There's 2 floors. We have my escalator going up and my escalator going down. Okay, so the initial reaction for my mall is when the little door right here, that's what mall doors look like, right? Okay, so when the doors open, people start coming in. The rate of change would be pretty fast because we started at 0. We had nobody in the mall. And for this made-up reaction, we're going to call this floor A. And this is floor B up here. So we had nobody, and then all of a sudden, people start coming in. We have a whole bunch of A, whole bunch of reactants. But usually the food court is up here on the top, and there's all the good stores seem to be on the top. So people start coming in, and then eventually they're going to go up. They're going to go up to the 2nd floor. Okay, and then once a whole bunch of people are up here, we're going to get this pattern of people going up and down the escalator. Okay, this isn't a very realistic example, but it works. So if I had 5 people, I'm not going to draw them, I'm just going to write 5. 5 people go up. If it's at equilibrium, how many people would come down? That's right, 5 people have to come back down. Okay, do the amounts of people on the 2nd floor and the 1st floor have to be the same for it to be at equilibrium? No. So if they go in, and let's say the better stores are up here, the more popular stores, I might have 100 people go in. Maybe only 40 of them are down here, and 60 of them are up here at the top. Okay, so if 5 people go up, this goes down to 35, this goes up to 65, but then 5 different people are going to come back down, and that would go down. That would go back up to 40, and this would go back down to 60. Okay, so this balance of the rate is what makes it equilibrium. Okay, and the dynamic part is it's not the same 40 people that are here, and it's not the same 60 people that are here. The people on each floor are changing. That's the dynamic part. In a reaction, the molecules are still reacting. So I will have A still turning into B. So the A's aren't all the same people. Okay, they're not all the same molecules. And the B's aren't all the same. They're going to keep going. So it's kind of like changing, but at the same time, it's constant. Okay, there's a balance point between them. Okay, so that's our dynamic equilibrium. And that's a really important concept for you guys to understand. Okay, so this is the math part. Whoops. This is the math part of the chapter. And it's actually not that bad. Okay, equilibrium constants are pretty easy calculations to do, even in AP Chem. Okay, we can get those equilibriums pretty easily. So here is our made-up reaction. Okay, and the N, M, and the X and the Y are the coefficients. So usually there's like 1, you know, if it's 1, it's not written, 2 or 3. They don't go up that high usually, but they can go up to like 6, okay, 10. Those are our coefficients, and A and B are my reactants in this new reaction, and C and D are my products, okay? So K, capital K, is a constant. A constant is just a number that doesn't change, like the speed of light. It's always 3 times 10 to the 8th power meters per second. Up here, my equilibrium constant, something that wouldn't change, since the amount, the concentration of A and B stays equal, I can find a ratio of these. Okay, let's use our 60-40. So if there were 60 B's, okay, there's 60 of these guys, and this went down to 40, that looks about right. This looks to be about 60-40. Okay, then the ratio of these two things is going to be constant because they stay constant. This one might go 59, 41, or it could go 61 and 39. They're going to go up and down a little bit, but the ratio is basically the same the whole time from everywhere from this point on. The ratio is going to be constant. Okay, so somebody decided that we were going to define the ratio as the product on top. So K for this reaction, and we put a little C down here to show that we're talking about the concentration, because you'll see in the next one we can do pressure as well, but C is for concentration. And then we know our brackets mean concentration, and I put the product on top, so B goes on top right here, and on the bottom I have my A. Concentration of A goes down here. Okay, and since these don't have any coefficients, they're both 1, that means there's no exponents. It's just 1 and 1. So what would this be? It would be 60 over 40. Okay, 60 over 40 would give me, let's see, we can cancel the zeros. 6 over 4, we can cancel a 2, that's 3 halves. And 3 halves is 1.5. So my K for this made-up problem is 1.5. Okay, so why is that important? Well, I can take any time that I want, and if it's at equilibrium, if I know K and I know one of the concentrations, I can find the other one. I can plug 1.5 in here, and I can plug the concentration of B in here, and I can find A. Or I could plug A in and the equilibrium constant, and I could find B. So that's why it's handy. And it also tells us something else that's really important, and that is the value of K tells us which side of this reaction is favored. Okay, meaning this is a ratio with products on top. So this 1.5 actually tells us something important. It tells us that the top is 1.5 times bigger than the bottom. the ratio of these two things is 1.5. So if I got 1, if it was 50-50, 1, that would tell me they're equal. That basically never happens. So it's almost never equal amounts. The products are usually bigger, or the reactants are usually bigger. And that tells us which side is favored. So this 1.5 means I have more product. So the product side is favored for this reaction. Okay, why would the product side be favored? Usually because they're more stable. Okay, so usually it has to do with the energy levels of A and B, and which is going to be more stable. And that tells us something about whether it's endo or exothermic. So that's very interesting. Okay, I'm going to pop back on and see if there's any questions over here that I cannot see. Nope. Remember, you guys can type them in the chat over here. So if you need anything, you can speak up if you want to, or you can type it right here. Okay?
Miss Fergus.
What's up?
Last time you were on this, you said you had chickens.
I do.
I was wondering if we could see the chickens one day.
Yes, definitely. Okay. But probably after I stop recording.
Okay.
Because you'll also see my messy backyard. No, it looks good. Definitely. All right.
Thank you.
You're welcome. That's an important question. Okay. So back over here, we have our equilibrium expression for our made-up reaction, where C and D are on top because they're the products, and then A and B are the reactants, so they go on the bottom. Sample problem A. So let's write out what this would be. That means that I have my product, I only have one, this guy. Oh no, battery's running low. I have to move it by the plug. No, I'll just move it over here. My husband's trying to save it. All right. So SO3 is going to go on top. SO3 copy goes on top. I don't have much longer. We're fine. And then we're going to go look at chickens. And concentration of this guy divided by, okay, so everything on the right over here is going to be making toast. Everything on the right side of this is going to be my reactant. So I have SO2. And notice I'm not taking the coefficient, just the formula. I'll go down here, paste. And then this one, that 2 actually becomes the exponent. So up here is a 2. Okay, and then times my other one, which is O2. I'll just type it, O2. And that's my equilibrium. So both of these things are on the bottom of the fraction, which is kind of hard to see from this. I would write it like this normally. Okay, so I have SO2 down here and O2 down here, and there's only one product, so the SO3 is up here. Okay, and then don't forget that this is squared. This 2 right here, nope. That 2, I was going to try to color code it, but that's going to take me too long. That 2 is this 2 right here. That's where that came from. Okay, I'm going to let you guys go ahead and write this one out on your own. Oh, I remember why I put this here. There is one little trick to these, and that is that if you have a pure liquid, or a pure solid, they cannot go in the equilibrium constant. They don't go into K. You leave out water because it's a pure liquid. And if you had a solid in there, you would leave that out too. And that just has to do with the concentration of a gas can change very easily when it's reacting. But if you have a solid thing, how many moles per liter are there? If you lose moles, you're losing liters. So the concentration technically doesn't change. So that's why we don't put that in there. Okay. So this would be my products over my reactants. And the exponents, since it looks like this is balanced, I have 4 hydrogens. This is all balanced, so they're all 1s. So all of the exponents are 1s. Okay. And then one of the last things I wanted to go over is what does the value of K tell us about the equilibrium? So this K is 798. And that means that when I write my equilibrium constant expression like this, the product over reactants, I'm going to get 798 as my constant, and that's a real constant. I looked that one up. So for that reaction right here, you're going to get 798. Let's just say 800. You get 800 times more product than you have reactant. So which side is favored? The product side, because you're making a lot more of it. For this reaction, this is an acid. You guys should see the hydrogen in front. Makes this an acid, and this was carbonate. So this is carbonic acid. And when you mix it with water, it's going to ionize into this hydronium. And this is bicarbonate. That hydrogen there makes the bicarbonate. And so these are aqueous, so these do go on top over this. Okay. I know I told you guys I was going to have you write it out, but I lied. I'm going to do it. So concentration of my product times this other guy. Copy right there. And then that whole thing divided by just this one guy. Because the water does not belong in the equilibrium constant because it is a pure liquid. So, whoops, make the bracket tiny. So this is my K, my equilibrium constant expression for the reaction, for this reaction up here. And it's an acid, but it's not on our strong acid list. It's a weak acid. So weak acids only partially ionize, and these are the ions it's going to form. So since it only partially ionizes, that means that I don't get very much of the product out. And how much do I get? You guys can look at the number, 4.2 times 10 to the negative 7. That is, what is that? 10 to the negative 6 would be a millionth. So that's a 10 millionth of the reactant. So I get 10 million times less of the product than I have of the reactant. Okay, that's the tiny, tiny, tiny amount. So this tiny number tells us that the right side is not favored. The left side is favored in this reaction, and I'm only going to form a tiny bit of these ions. That tiny bit still is going to change the pH. So if you put carbonic acid in water, you still are going to have it be a pH less than 7, but it's not going to be very much. Okay, so that's how we tell whether it lies to the right or it lies to the left. That just means, does it favor the reactant side or the product side? Okay, and you can tell by what the number is. All right, so you guys try these problems out on your own, and you guys can always email me if you have questions. Does anybody have questions about 18.1? I see one comment. Yay. And then I see a thumbs down. That means no questions. Okay, I'm going to stop recording. If you guys do have questions, you can ask me then. Stop.